Okay. Oh, that sounds great. Okay. Yeah, so tomorrow afternoon probably. Okay. Yeah, sounds good. Tomorrow afternoon or Wednesday morning. Okay, got it. All right, thank you. All right, bye. Yeah, should work.
You have to wait just the 2 days.
Yeah, I think so.
Yeah, the exam is on Wednesday. Well, now you're ready. You don't have to study anymore.
Could you seem to be done with both my chair and my sofa example on Wednesday morning? Wednesday morning, got it. Is that okay? Yes.
We need to finish up a little bit from lecture notes 11, mostly just the MATLAB implementation of MATLAB example. And then after that, we'll jump to 12.
Really chill.
So I think probably we'll spend maybe about half the time on 11 and the other half on 12.
I think it'll be fine. It's a retirement home. Okay. Oh yeah, yeah. Okay, that's good. Thanks. Bye.
All right, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone feeling today? Tired, stressed? It is hot, yeah. Weather's definitely heating up. Summer's on the way. Yeah, yeah, I know. Yeah, so we have our midterm this week, and so it's not today. It's Wednesday, and so we have that coming up. So I'm sure probably you guys are pretty stressed about that. And so I know I made a couple of mistakes in the review videos, so I apologize for that. I just kind of flipped some of the signs around. But if you're on the Discord server and you're kind of following the questions chat, then hopefully I cleared up some of those mistakes, right? So I apologize. I know probably that was probably pretty confusing about where to put the negatives and things like that, but hopefully that cleared things up. Right? Okay, so today we're going to finish up the last bit of lecture notes 11 from last time. mostly just the MATLAB implementation of the convection diffusion codes with finite volumes in 2D. Okay, and so we're going to go through that MATLAB code. Hopefully, this makes hopefully going through this will make finite volumes make a little bit more sense, because I think this code is better structured than the one I gave you before with just diffusion. Okay, and then after that, we're going to start lecture notes 12. Where we go over higher order schemes. So that's kind of, for many of you, that's kind of the last piece of the puzzle that you need before you can finally have everything you need for the project. Okay? Because if you remember for the project, one of the big things is that, what I want you to do is I want you to change the convection scheme from kind of a basic central difference to a higher order scheme to kind of get rid of that cross-stream diffusion. Okay? So today we'll kind of introduce the idea of that. And then kind of go over, why you would do this and how you would do that. And then if we have time, kind of go over one example of that at the end. Okay. So that's the plan for today. So are there any questions before we get started? I did get a haircut. Yes. Perfect for the hot weather. No, the test is not today. The test is Wednesday. Mm-hmm. Yeah. So on Wednesday, before I kind of forget. So in my last class, I didn't mention it till the end, but so Wednesday, we're going to do the same thing as the last exam. And so if you want to come in on the Zoom call and ask questions, you're certainly welcome to do so, but it's not a requirement. And so if you'd rather, stay off the Zoom call and then just kind of work in peace for those 90 minutes, that's perfectly fine, right? But it's a 90-minute exam, and so you're going to have from 5:30 until 7 to finish the exam. Okay. Barring some special accommodations too. And so, anything I gave you for the first exam, if I talk to you personally for that, then that also applies for this exam too. Okay. Okay. All right. Any final questions before we get started again? Okay. All right. So to start today, I actually want to go back to the last set of lecture notes that we had. Just because there was it's a little bit easier than kind of writing things down again. Okay. And I want to come to this page right here. Right? Or let me step back a couple first. Right? Because what we're doing right now is we're doing these kinds of problems. We're doing 2D convection and diffusion with finite volumes, right? And so right here at the top here, we have our starting equation. And so we have our convection term, we have our diffusion term, and we have our source term, right? And so just like we always do with finite volumes, the way we're going to start is we're going to integrate this entire equation over a cell, right? And then we're going to use divergence theorem to convert these into boundary integrals, right? Or face integrals. That's what we're calling it, face integrals, okay? So I'm just kind of quickly reviewing where we left off last Wednesday, and so you don't have to write any of this down because this is literally the exact same notes that we had last week. Okay? Right, and then what we did was that since we're integrating over all the faces of our cell, we broke it up into 4 different integrals, right? And so we broke it up into a north face integral, an east face, a south, and a west face. Okay, and then what we did was we kind of integrated, or we took each of these integrals individually, and we evaluated their terms based on what the gradient is going to be over there, based on what the normal vector is, and based on the convection velocity, right? And so for our east face, we have this expression here. For our south face, we have this one here, and for our west face here, okay. And our north one, we have this one here, okay. And so in the end, once we plug in all the approximations and all of the finite differences, we end up with the following 4 expressions for the 4 integrals, right? And so we have the east face is equal to u phi, or u delta divided by 2 minus k. That's the coefficient in front of phi east, which is our east neighbor, plus u delta divided by 2 plus k. That's the coefficient for phi sub c, which is the centroid neighbor, okay, or yourself, the center cell, right? And then we have the south and the west and the north, right? And so I broke it up like this so that you can kind of see individually what each integral is contributing to the whole thing, right? And if you wanted to get like an overall, one algebraic equation for this, all you would have to do is just kind of add these up together, okay? Right, and that's what we have with this note right here. Right? Okay. And so the algebraic equation that we actually plug into the matrix set is basically the sum of all of these guys put together. But for now, I'm just going to leave it like this because the way I've kind of structured the example code for you is I'm going to evaluate each of these integrals individually, right? And so, take a screenshot of this, or it's just kind of, just kind of remember each of these coefficients and what they're correlated to each of the, how they're correlated to each of the face integrals, because you're going to see this exact form in the code. But the other thing that we have to take into account for is the fact that, our cell might sit on a boundary of the domain, right? And so, the way that we're handling these things is that, if we take each of the four integrals to, one by one, the north, the south, the east, and the west, we're going to replace that integral with the boundary value expression or boundary condition expression, if we're bordering that boundary, leaving all the other ones the same, okay? And so, here's an example where if you have a boundary condition on the north face, okay, a Dirichlet one, and here's an example if you have a Neumann condition on the east face, right? And so for Neumann condition, remember, we replace that entire integral. Okay, and so that's just kind of a brief recap over what we did last week. And so let's go back to our lecture notes for this week. Okay, and then let's do an example just to kind of put all this stuff together. All right, and so let's work on this following equation. So let's work with 50 partial phi partial x plus 5 partial phi partial y is equal to 2 partial squared phi partial x squared plus partial squared phi partial y squared plus 3xy. Okay. And then we're going to solve this equation on the following domain. Okay, so we have a total square domain. Okay. Right, on the south boundary of the domain, we have a zero flux boundary condition. And so we're going to say the flux is equal to 0. And so that's our Neumann condition on the south face, on the south boundary. Okay. On the left boundary, what we have is a Dirichlet boundary condition where our phi value is equal to 50. On the east boundary, we have phi is equal to 25. And on the north boundary, we have phi is equal to 50. Okay. And then for the sake of this example, let's go ahead and break up this domain into 16 finite volumes. Right, just like that. So we have volume 1, 2, 3, 4, all the way up to 16. Okay. Right. And so what we're going to do is we're going to write down the algebraic equations for certain cells. Okay. Right. And in particular, let's just do a few of them just so you kind of get the idea. Okay, so let's do four of them. And so let's do an interior cell. So let's do cell number 7. Okay. Let's do one on the south face. So let's do cell number 2. Okay. Let's do one on the west face. So let's do cell number 9. And let's do one in the corner. So let's do cell number 16. Okay. So let's do 7, 2, 9, 16. And we'll do it in that order because, first I want to show you an interior cell, and then I'll show you how to modify the conditions for a boundary condition. Okay. All right. And so before we move forward, let's go ahead and write down all the parameter values. And so let's write down our value for u, which is our x component of the velocity. And so our u value here is 50. Okay. Our v is 5. Okay, so that's the y velocity. Our k here is 2. Okay, because on the right-hand side, and we'll work with the delta or grid spacing of 0.25. Okay. All right. And so we're going to evaluate each of the integral expressions, for each of the cells, right? And so for cell 2, we're going to evaluate each of the 4 face integrals and then add them together in order to get the expression. Okay. Okay. So any questions on the setup for this example? Right, question. Yeah, it's a little bit. Yeah, the image here looks a little bit like Sudoku. Yeah, Sudoku is only a Sudoku is each one's only 3 by 3, and then the whole thing is 9 by 9. Yeah. Okay, so let's go ahead and start with cell number 7. All right, so cell 7 is an interior cell, and so we have neighbors on all sides. Okay. And so when we have neighbors on all sides, what we can do is we can take each of the face integrals and then keep them in their base form. All right, so let's write down each of the integrals. And so I'm going to start with the east integral, then the north one, then let's do the west one, and then the south one. Right. And so all of these are going to take their kind of basic forms here. All right. And so let's look back at the previous set of lecture notes just to remind ourselves and to remind me what those forms are, because I didn't have it written down. Okay. Okay, and so the base form here for the east integral we can see is u delta divided by 2 minus k phi east, and then the times phi sub east, and then plus u delta divided by 2 plus k phi sub c, right? So let's go ahead and put that in. Right, so for the east integral we have u delta divided by 2 plus k, okay, or minus k, sorry, minus k phi sub east, right? And so we have to look at the east neighbor for cell 7, and so that's going to be cell 8, right? So this is u delta divided by 2 minus k phi east, okay, which is phi 8, plus u delta divided by 2 plus k phi sub c, which is phi 7, okay? All right, and so let's go ahead and plug in the numbers for these guys. And so u delta, so u is 50 times 0.25 divided by 2 minus k. This is 4.25. Okay. And then we have u delta 50 times 0.25 divided by 2 plus k is 8.25. Okay. And so that's the first equation there. Okay. Now let's do the north integral. And so the north integral, the expression for that is v delta divided by 2 minus k phi north. And so the north neighbor for cell 7 here is going to be cell 11. Okay. Plus same thing here. And so we have v delta divided by 2 plus k, sorry, phi 7. Okay. And so let's go ahead and plug in the numbers for this. So we have 5 times 0.25 divided by 2 minus 2. Okay. And so for this, we have a minus 1.375. Okay. And then we have v delta divided by 2 plus k. And so we have v, which is 5 times 0.25 divided by 2 plus 2. And so this is a 2.625 phi 7. Okay. All right, so let's go ahead and go ahead and fill in the rest. So we have phi west here, and so phi west is going to be a minus u delta divided by 2 minus k. The west neighbor for cell 7 here is going to be cell 6, okay, plus a minus u delta divided by 2 plus k phi 7, okay. So let's go ahead and plug in the numbers for that. So minus 50 divided by 2 times 0.25 minus 2. Okay. And so this is a minus 8.25. Okay. And then we have the same thing over here. So we have minus 50 divided by 2 times 0.25 plus 2. And so we have a minus 4.25. Okay. And then for the south integral, what we have is minus v delta divided by 2 minus k. Okay. Times phi south neighbor. So south neighbor is 3. Okay. Plus a minus v delta divided by 2 plus k phi 7. Okay. And so let's go ahead and perform that math. And so we have minus 5 divided by 2 times 0.25 minus 2. Okay. And so we have minus 2.625. Okay. And then on the right here, we have a minus 5 for v times 0.25 divided by 2 plus 2. And so we have a positive 1.375. Okay. All right. And then to finally get our algebraic equation, all we have to do is just kind of add up all of these together, right? And so we have a 4.25 phi 8 minus 1.375 phi 11 minus 8.25 phi 6 minus 2.625 phi 3, okay? And if we add up all the coefficients for phi 7, we have 8.25 plus 2.625 minus 4.225 plus 1.375. I just accidentally deleted that. 2.625. Right, and we end up with 8 phi 7. Right, and so that's the algebraic equation for cell 7, right? And so it's a little bit time consuming, I know, to write out each of the different integrals here. But what you'll see is that this makes things work out pretty well, okay? And the reason I started with an interior cell here is that, now that we know, the base coefficients for each of these, because u and k and v, they're all the same for all the different cells. All we have to do here is just kind of swap out the different phi indices, and then replace the integrals for a boundary condition where necessary. Okay, so any questions on how we got these equations so far? Okay. All right, and so what was the next one that we wanted? So we wanted cell number 2 next, right? And so cell 2, we have a Neumann boundary condition on the south face. Okay. And so what that's going to tell us to do is that's going to tell us to replace the south integral. Yeah, so yes, so if you're following along in the notes, I think I made some typos when I made those notes, and so I think these ones should be correct because I just punched them in right now. Yeah. Yeah, I think I might have forgotten to divide the velocities by 2 when I computed those numbers. Yeah. Mm-hmm. Yeah. So it's yeah. So don't listen to the notes. I think I might have punched those in a little bit too quickly. But let me go ahead and verify some of these just to make sure. Right. So let me do the north integral again. And so the north integral, we have 50. Let's see, 50. Oh no, 5 times 0.25 divided by 2 minus 2. Yep. And so that's minus 1.375. And then let me do the west one, right? So the west one, we have minus 50 times 0.25 divided by 2 minus k. Yep, so that's minus 8.25. So these ones should be correct, more over the one that's in the notes right now. Yep. Mm-hmm. All right, so you got 6.25 for phi 8. So phi 8, remember phi 8, the coefficient in front of here, this is u delta divided by 2 minus k, right? Positive u delta divided by 2. And so u here is 50, right? And so we do 50 times delta. So delta is 0.25, okay, divided by 2, right? And then we do minus k. So we do minus 2 here for k, okay? All right, and so if we perform this, we get 50 times 0.25 divided by 2 minus k, minus 2. It should be 4.25. Yeah. Mm-hmm. Okay. All right, so let's do cell number 2. So cell number 2 has a Neumann BC on the south face. And so what this is going to tell us is that we're going to replace the south integral with the Neumann BC. Okay, and so let me write down each of the different integrals again, right? Okay. And I'm going to use the same coefficients that I got on the previous page, but replace them with cell 2's neighbors, right? And so for the east integral, we have a 4.25 times the east neighbor. And so the east neighbor for 2 is going to be phi 3, okay? And then we have plus 8.25 times phi c, which is 2, okay? Then we go to the north integral. And the north integral, the first coefficient there is a minus 1.375, okay? The north neighbor for cell 2 should be cell 6, okay? Right. Plus the same coefficient for phi c, which is 2.625, phi 2, okay? For the west integral, we have a minus 8.25 times the west neighbor. So the west neighbor for cell 2 is cell 1, okay? Plus, or minus, I should say, minus 4.25 phi sub 2, okay? Right, and so now the difference here is that instead of using the coefficients from the previous page on phi sub south, what we can do here is just replace this with the Neumann BC. And we know from the problem that the south face or the south boundary has a flux boundary condition of 0. And so all we have to do is just replace this entire integral with just 0 right here. Okay. All right, and so just like before, now that we've evaluated the 4 integrals, let's go ahead and add up their values. And so we have a 4.25 phi 3 minus 1.375 phi 6 minus 8.25 phi 1, okay? And then we're going to add together all of the phi 2 terms. We have 8.25 plus 2.625 minus 4.25. And so this gives us a positive 6.625 phi 2, okay? Right? And so that's how you do the south one, okay? Oh, actually, before I forget too. So the we also need the source term as well, right? So on the right here, we have equal to q of xc yc delta squared. Okay. So I'm not going to evaluate that for this one because it's because I know you guys know how to do that, but I wanted to focus on just the four integrals here, just so that we kind of make sure we get that down. Okay. Okay. And so any questions on this so far? Okay. And just like I mentioned in the midterm review, like you can use this four integrals method for the midterm too. So when I ask you to find the finite volume equations for just diffusion, you can actually use this exact same process. It's just that you would set both the convection velocity to 0, and I think that's kind of what I did in the midterm review as well. Okay. Okay. So our next cell, and so I think our next cell was cell number 9. And so cell 9 right here, we have a Dirichlet boundary condition on the west face. Okay. And so we're going to replace the west integral with an expression that has the Dirichlet boundary condition. Okay. So this is technically in the midterm. You can use the same process for the mid. Not this problem obviously is not going to be in there, but this process you can use exactly for the midterm. Yeah. If you set all the convection velocity to 0, of course. All right. And so we have our four integrals here. And so the one that we want to replace is the west one. So let me go ahead and fill in all the other ones. Okay. All right. And so for the east integral, this stays the same. And so we have a 4.25 times the east neighbor for cell 9, which is cell 10, right? And so we have a, what is it, minus plus 8.25 phi 9, okay? Then we have the north integral. I think the north integral is minus 1.375 plus the north neighbor for cell 9, which is cell 13, right? Plus 2.625 times phi c, so that's phi 9, okay? The west integral we're going to change, and so I'll leave that for last. And then the south integral, what we have here is a minus 2.625 times the south neighbor. And so the south neighbor for cell 9 is cell 5, okay? And we're going to add a positive 1.375 phi 9, okay? All right, and so that's all the normal neighbor cells. And so now let's account for the Dirichlet boundary condition. Okay, and so for the Dirichlet boundary condition, let's look back on our notes from last time to see what we have to do here. Okay, so for Dirichlet boundary condition, remember we have to make kind of two replacements, right? And so the first replacement is has to do with the fact that we know the value of phi on the boundary, okay? And so we're gonna have one term that's phi naught times the velocity times the delta, okay? And then we also have a minus k, minus 2k phi naught that comes from the diffusion term, okay? All right, and so let's kind of picture this. And then let's go ahead and plug that into our case. Okay. All right, and so first we have a minus 2k times phi sub c, okay? And so phi sub c is c9, okay? Then we're going to add together. Let me do this actually. Let me go ahead and do the whole integral from the beginning, okay? Because for this west integral term, what we have is the following. So we have a minus, let's see, a minus VU times phi sub W, little w, okay, plus K partial phi partial X on the west face, okay, times delta, right? Because I don't want to mess up the sign again, and so I want to kind of start this from the beginning, because for the west face integral, remember we have a minus that's out in front of the of this convection term, okay, and so I want to make sure that I don't mess that up, okay. And so let's kind of take this kind of step by step when as we account for the Dirichlet boundary condition. And so the first thing that we do is we change phi sub little w here. We change this to the Dirichlet condition, right? And so this can be phi naught, okay? And then from here, what we're going to do is we're going to replace this diffusion term. And so instead of partial phi partial x, what we have here is partial phi sub c minus phi sub o, okay, divided by delta divided by 2, right? Because we're on the on that west face, okay, and we only travel half that distance. All right, and so if we work this out, and then what we get is a minus u phi naught delta, okay, plus 2k phi sub c, okay, minus 2k phi naught, okay. Okay, and so that's the that's what we get there. And so remember, you have to be careful about the sign of the convection term, because that depends on which face that you're on. Okay, and so now that we have that expression there, we can go ahead and plug in for it. Okay. And so at first we have a minus u, so minus 50 times delta 0.25 times the phi naught value. So the phi naught value is also 50. Okay. And so at first we have a minus 625, okay, right? And so that's the first term, and so that's the minus u phi naught delta plus 2k phi sub c, and so k here is 2, and so we have plus 4 phi sub c, okay, which phi sub c in this case is phi 9, right? And we have a minus 2k times phi naught, and so we have minus 2 times 50, which is phi naught, times 2, which is k, and so we have a minus 200. Okay. All right. And so now that we have each of these integrals, let's go ahead and add up all their values together. Okay. And so we have a 4.25 phi 10. Minus 1.375 phi 13, okay, minus 2.625 phi 5, okay, so let's add up all the phi 9 values. So we have 8.25 plus 2.625 plus 1.375, so we have plus 12.25 phi 9, okay, oh, plus 4, sorry, and so this is actually 16. Plus 16.25 phi 9, okay? And then we have our constant term, so we have a minus 825 as well. Right? And so that's our algebraic equation for cell number 9. And of course, since this thing is a constant, we can move that to the right-hand side. Okay. All right. And so things are a little bit difficult when you do the Dirichlet boundary conditions. You want to make sure that you have the right signs for everything. But once you do that, it follows the same process where you just add up. You keep all the other integrals the same. You add up all their values, and then that's how you get that. Okay. Okay. So any questions on this part of the example here? Okay. All right. And so let's do the final cell here that we specified, just so that you guys get a sense for what to do for the corners. And so let's do cell number 16. Okay. All right. And so cell 16 is a corner cell. Okay. And for the corner cells, remember, we're going to replace two of the integrals, right? And so particular, since cell 16 sits at kind of the northeast of our domain, right? And so it's where main would be if our domain was the US map. And so we're going to replace the north integral and the east integral with Dirichlet boundary conditions. Okay. Let's go ahead and write down all our integrals again.
Professor, I'm sorry, but could you go back to the last page for a second? I'm just
Sure.
going to snap a quick.
Mm-hmm.
My phone will load. All right. Thank you.
Yep. Right. All right. Okay, so we have our four integrals just like before. And so let's evaluate the west and the south ones because we actually do have neighbors there, right? And so for the west integral, let me go back a couple. We have a minus 8.25 and a minus 4.25. Right? Okay. And so we have minus 8.25 times the west neighbor. So the west neighbor for cell 16 is cell 15. Okay. And the minus 4.25 phi sub c, which is cell 16. Okay. And then for the south integral, what we have is a minus 6.25 plus 1.375. So minus 2.625 south neighbor, which is phi 12, plus 1.375 phi sub c, which is phi 16. Okay. All right, question. So would it be possible to go over a corner cell that is Dirichlet and Neumann as well? Yeah, we can do that real quick. So we can do cell number 4. And so cell 4 has a Neumann and a Dirichlet BC on that. Yeah, so we'll do that after this. Yep. Okay, and so let's do the east. Let's do the east neighbor first. So east is normally we have our integral look like this. So we have u times phi little e minus k partial phi partial x on the east face, okay? And so this is going to become u phi naught positive minus k phi naught minus phi sub c divided by delta divided by 2. Okay. We're going to multiply the whole thing by delta here. Okay. Right. And so in the end, what we get is a u delta phi naught, u delta phi naught, okay, minus minus k, or minus 2k phi naught plus 2k phi sub c. You guys hear my cat? Okay, and so let's go ahead and plug in. The values for this, right? And so we have u times delta, 50 times 0.25 times phi naught. And so you have to be careful here so that you use the right phi value or the right Dirichlet boundary condition value. And so for the east face here, we have a boundary condition of 25, right? And so this is going to be 50. Or let's see, this is 25 for east boundary. Okay. right? And so you want to make sure you use the right Dirichlet boundary condition value, okay? And so we have 50 times 0.25 times 25. Okay, and so this is 312, 312.5, okay? Then we have a minus 2 times k, which is 2, times phi naught, which is 25. And so we have a minus 100, okay? Plus 4, which is 2 times 2 times phi sub c, which is phi 16, okay? All right. And so for the north integral, we have a very similar expression here. And so, but instead of u, we have v, positive v here, okay? So we have v delta times phi naught, okay? Minus 2k phi naught plus 2k phi sub c, which is phi 16, okay? Okay, and so let's go ahead and plug in the values for that. And so we have v is equal to 5 times 0.25 times the north boundary condition, right? And so this phi naught here is going to be 50 for the north boundary. Okay. And so we have 5 times 0.25 times 50. Okay, so that's 62.5. Okay, minus 2 times k times phi naught. So we have minus 2 times 50. So that's a minus 200. Okay, and we have plus 4 phi 16. Okay. And so now we can add all of these guys together. And so we have a minus 8.25 phi 15 minus 2.625 phi 12. Okay. And then let's add up all this, the phi 16 values. And so we have 4 plus 4 minus 4.25 plus 1.375. And so we have a plus 5.125 phi 16, okay? And then we're going to add up all of our other constants here, okay? And so we have plus this one, minus this, plus this, minus this, right? So we have 312.5 minus 100 plus 62.5 minus 200, and we get is a positive 75, which we, of course, move over to the right-hand side. Okay. Okay, and so that's what you do when you have two Dirichlet boundary conditions, that you replace two of these integrals with, with the boundary expressions. Okay. All right. So any questions on this? Okay, so let's do one more, and so let's do an example where you have both a Dirichlet and a Neumann boundary condition going on at the same time. And so I think we can either do cell number 1 or we can do cell 4. And so let's do cell 4, because that's what I said 5 minutes ago. Okay. All right, so cell 4. So cell 4 here, we have a Neumann condition on the south face and a Dirichlet condition on the east face. Okay. And so let's go ahead and write down our integrals again. Okay, so let's do the east integral first, because this is going to look the same as the 16 one, as a cell 16, right? And so for this one, we have a positive u delta phi naught, okay, and we have a minus 2k phi naught plus 2k phi sub c, where phi sub c here is 4, okay, right? Got those signs right? Yes. Okay, so let's go ahead and plug in the numbers for this. So we have U, which is 50, times delta here, which is 0.25, times the Dirichlet value on that east face, which is 25. Okay, so we have a 312.5. Okay, then we have a minus 2 times 2 times the Dirichlet value here, which is 25. Okay, so we have a minus 100. Okay, plus 2 times k times phi naught, so that's a 4 phi 4. Phi sub c, sorry. Okay. Right. And so that's the hard one. That's our Dirichlet boundary condition. And so now let's go ahead and fill in the rest of them. And so for the north integral here, we have just our usual case. I think I have to go back a couple to see what the coefficients are. Right. And so we have a minus 1.375 and a positive 2.625. Okay. Okay. Minus 1.375 times the north neighbor. North neighbor for cell 4 is cell 8. Okay. Plus 2.625 phi 4. Okay. Now let's do the west integral. And so the coefficients for the west integral are a minus 8.25 and a minus 4.25. Okay, west neighbor for cell 4 is cell 3, minus 4.25, cell 4 for phi sub c. Okay. Then we come to our south integral, but our south integral here is just 0, right? Because we have a 0 flux boundary condition on the south face. And so that's just going to be a 0 right there. Okay. All right, and so let's go ahead and add up all of these guys. And so what we get is a minus 1.375 phi 8 minus 8.25 phi 3. Okay. Let's add up all the phi 4 terms. And so the phi 4s, we have a positive 4 plus 2.625 minus 4.25. Okay. Plus 2.375, okay, phi 4, and then we're going to add together our constant terms, which is 312.5 and minus 100, and so this can be a positive 212.5, where of course we're going to move this to the right hand side. Okay. All right, and so that's how you deal with a case where you have both a Dirichlet and a Neumann boundary condition, right? And so you'd follow the same process. You write out each of the 4 integrals. It's just that you make different substitutions for each one, depending on what type of boundary you have there. Okay. Okay. And so any questions on this before we jump into the code? Okay. And so that took a little bit longer than I thought, but actually I think it's good. And so I think we did a very thorough job here of going through cell by cell. What do we do with each of the different integrals here? Okay. And so now that you've kind of seen kind of the logic worked out by hand, I think seeing that in MATLAB I think should be it should make a little bit more sense than what we had before. Okay. So let me go ahead and share my screen. Right. And so here is the code that I've posted onto Canvas for you guys. Okay. And so the name of this code, so I've posted 2 right now. And so the name of this code, let me check real quick. The name of this code is 2D Convection Diffusion FVM example. Okay. And so this is basically our finite volume example for convection diffusion. Right. And so let's take a look. Okay. And so the beginning portion is just all the variables, yada, yada, yada. That's fine. Okay. And then we enter the loop here. Okay. So this is kind of where all the meat and potatoes are. Okay. All right. And so the first thing you see here is that we have our nested for loop. Okay. And so the purpose of the nested for loop is to visit every single cell in our grid. Okay. So that's nothing new. And so that's, we see that in every single one of our 2D codes, right? And then we have another set of code here to compute the ID numbers. Right? And so whenever you have a 2D domain here, you always have to have this mapping between, what are kind of the I and j coordinates of the cell, and what is the numerical ID for that cell. Okay. We can talk about that after the class. Yep. Okay. And so from here, you can see I've launched into 4 different if statements here. Okay. And so you can see I have one if statement here for the east integral. Fortunately, I do think it's a little bit, I guess I rotated clockwise around the cell. And so I have east integral, south integral, west integral, and north integral. Okay. So let's kind of go through each of these integrals kind of one by one. And so you can kind of see what's going on. Okay. So let's start with the east one. Right? And so the east one here, I have 2 different cases that we need to talk about, right? And so let's look at the else statement first, right? Because the else statement, what this is for is for the case when the east face faces an interior, right? And so our east face faces an interior, then we have an east neighbor, right? And so what you can see from here is that I've added the base case coefficients here, right? And so first we have a at my ID, and so this is the coefficient for phi sub c only for the east integral, right? And so for the east integral, this is a plus u delta divided by 2 plus k. And then on the for the east neighbor here, so we have a my ID east ID is equal to a my ID east ID plus u delta divided by 2 minus k. Okay. And so these coefficients here, this one and this one, these are lifted kind of straight off from the hand calculations. Okay. Okay. And so that's the interior case. And so now let's look at the case when we're on a boundary, okay? And so if our cell is on the total right side of the domain, then what we're going to do is we're going to apply our Dirichlet boundary condition, okay? Okay. All right, so first thing we have to do is we have to add in the contributions to phi sub c, right? And so the contribution to phi sub c is a plus 2k times phi c, right? And so that's why we have a my ID is equal to a my ID plus 2k, right? And so that's the plus 2k that we get from the center cell. Okay? Then you have the contributions to the right hand side, right? And so the contributions to the right hand side, if you remember, was a velocity term, which was a u delta times phi naught, and then a minus 2k times phi naught. Okay. And so if you compare what I have here compared to what we just kind of did the calculations for. So if you compare this to like cell 16 or to cell cell number 4, right? You can see that the signs for these are reversed, right? And so for cell number 4 and for cell 16, I had a positive u delta phi naught and a minus 2k phi naught, right? But since we're moving these terms over to the right hand side, and we're basically subtracting those terms from both sides, then the signs for these guys flip. And so instead of a positive u delta phi naught, we have a minus u delta phi naught. And instead of a negative 2k phi naught, we have a positive 2k phi naught. Okay. Right. And so remember, the sign change is because we're moving it kind of to the other side of the algebraic equation, where now it's going to be part of the b vector instead of the a vector or a matrix. Okay. All right. Does that make sense about why we change the signs for these guys when we move it to the right hand side? Right. Okay. Okay. So that's the east integral. And so once you understand the east integral, the rest are basically the same. And so let's look at the south integral here. And so for the south integral, you remember that's integral with south. Okay. And so first let's do the base case where we're on an interior cell. So for an interior cell, we have a minus v delta divided by 2 plus k. That's for phi sub c. And then for phi sub s, we have a minus v delta divided by 2 minus k, right? And so that's the coefficient for that. Okay. And then if we're on the south boundary, so if j is equal to 1, then we account for the Neumann boundary condition. But the Neumann boundary condition here is super simple. It's just going to be 0, okay, because we have 0 flux. Okay. All right. And so that's the south integral. West integral is exactly the same. And so for the west integral, if we're on the interior, we have a minus u delta divided by 2 plus k. That's for phi sub c. And so that goes into a my ID, okay? And then for the west neighbor, we have a minus U delta divided by 2 minus K, right? And so that's why it's A my ID west ID, A my ID west ID. Okay? And then if we're on the west boundary, so if I is equal to 1, then we're going to account for the Dirichlet boundary condition. And so the Dirichlet boundary condition on the west face is 50, okay? Then we're going to add a positive U delta plus 2 times K, right? All right. And then finally, we have the north integral. And for the north integral, if we're on the interior, we have a positive V delta divided by 2 plus K, and then a positive V delta divided by 2 minus K. And that's the coefficients for phi sub C and phi sub N, okay? And then if we're on a boundary, so if J equal to NY, which is the very top of the domain, then we account for that in the boundary conditions here. And so we have 50 times a negative V d, delta plus 50 times 2 times K. Okay. Right. And so, you know, I know kind of the last example, you know, all the hand calculations were pretty tedious because we separated them into integrals there. But, you know, you can see here this is the reason why. And so if you kind of formulate it out like that and kind of think of finite volumes in terms of, you know, I have to evaluate each of the 4 integrals, then implementing that into code is pretty simple, because you can see we've done the exact same thing here, where we've broken it up into the east integral, the south integral, the west integral, and the north integral. All right, any questions on this so far? Okay. All right, and then the last thing we have to do here is we have to incorporate the forcing function, and so that's kind of the last thing that I kind of ignored. Okay. And so our forcing function in this case was 3xy, okay? And so to compute that, we have to compute the x position of the cell. We have to compute the y position of the cell based on the I and j coordinates, right? Because remember, this is physical x, physical y. And then to this, we're going to add 3 times x times y, which is the q. This is the q value for this function. And then we multiply by delta times delta, or delta squared, because we're doing our trapezoidal rule, okay? All right, and then from there, you know, our linear system will be set, and so we just have to solve it just like we usually do, and then we can display the results, okay? All right, and so for in this problem, it looks something like this, okay? All right, so any final questions on this code before we kind of move on to the next thing? Okay. All right, so that's the example that I have for you for 2D convection diffusion with finite volumes. Okay, so this code is fully worked out, and it works in its entirety. And so if you download that code, run it in MATLAB, you'll get the same thing as I did. Okay, and so use this code together with kind of a lot of the hand calculations we just did, so that you can you know, so that you can kind of better understand convection diffusion. Okay. So let me do one thing actually. So let me go ahead and let's crank this up to 75 by 75, and let's see kind of a fine version of this solution. Okay. Okay. So if you refine the grid, then it looks a little better like that. Okay. So let's go back to the iPad. Right. So we have 15 more minutes, and so I think that's enough time to just kind of barely start, you know, what we're doing with higher order schemes. Okay. All right, and so now we're going to start lecture notes 12 here, and this is higher order convection schemes. Okay. And so this whole unit is basically, you know, is basically going to teach us how do we use a better way to discretize the convective term. Okay. Because if you kind of remember when we first started going over convection with finite differences, we saw that the convection term has a lot of problems, right? Convection terms literally have 99 problems. And you can probably complete the lyrics for that one, and it would be true for convection terms as well, right? And so let's kind of review some of the problems that the convection term has, right? So the first problem that we ran into was this problem of stability. Okay? And so with stability, remember, whenever we have a phenomenon with convection, and if we use a central scheme to model that convection, okay. If we use a central difference scheme to model the convection, then our solution can sometimes go unstable. Okay. Okay. And the main reason it went unstable is because the grid isn't refined enough. So if you remember, we had that number called the Peclet number, and so if the Peclet number was greater than 2, then we got instability. Okay. But for now, I'm just going to say is we can go unstable if the mesh is not refined enough. Okay. And so kind of visually, remember what instability looks like is that if normally you should get a nice kind of smooth solution like this, right? If we have an instability, it's going to look something like this. Right? It's going to do all these kind of crazy Simpson hair, Bart hair patterns, right? Which we don't want, right? So we don't want these things because, in reality, things don't really behave like this. Okay? And so this was bad. And so the way that we kind of dealt with this was that we either, one thing is we could either refine the mesh, and so we can just kind of reduce the cell size or reduce the delta until, our Peclet number is less than 2, right? That's one way that we could deal with it. Or we could have changed to an upwinding scheme. And so we could change to either like a forward difference or a backward difference, or kind of the equivalence in finite volumes as well, okay? And that helped us deal with convection, okay? But this is a problem because, because right now we kind of have to make a choice where, there's really no perfect solution, right? Because if we refine the grid, that makes things stable, but, it's going to make our solution more expensive, right? We can switch to upwinding, which is good, but, the upwinding schemes have a lower accuracy, and so they're not that desirable, okay? And so, no matter what, you're going to be trading something off here. And so, this kind of begs the question of, if there's kind of something better that we can do to kind of deal with this instability. Okay. So any questions on this so far? Okay. And so that's one big problem that we had with diffusion. I mean, with convection was that, we had the stability problem. Okay? Another big problem that we had, and this was kind of unique to just 2D and 3D convection. Okay? And that was this idea of cross-stream diffusion. Right. And so the idea with cross-stream diffusion is that if you have a convection velocity that does not align with the grid, if the convection velocity doesn't align with the grid, you can have what's called an artificial diffusion that shows up in your problem that basically, you know, boosts the amount of diffusion that you have, which is not what you want. Okay. And so just to kind of draw you a picture, let's say that we have a grid that looks like this. Okay. And so this could be a finite difference grid or it could be a finite volume grid. Okay. And so if you have a convection velocity that goes like this, okay, then what's going to happen is then we're going to have some additional diffusion that we don't want to see in the problem. Okay. All right. And so what we're going to do this week, or I guess, you know, today and next week, because we have the midterm on Wednesday, is we're mostly going to deal with this second issue. Okay. Okay. So higher order scheme, it'll help a little bit with stability, but it doesn't help too much. And so it's, you can still go unstable with higher order schemes, but, being able to eliminate this cross stream diffusion is huge, right? And so whenever you have a case where, because basically right now, the way that you guys are doing, convection diffusion is that whenever you have a velocity that for any time it kind of goes, skew to the grid like this, you're going to accumulate tons and tons of errors because it's, you have this cross-stream diffusion that just kind of keeps growing and growing, right? And so this is a really big issue, especially, if you're running like a very large simulation that's going to take place over a long time. You don't want to keep accumulating these kinds of diffusion because then it's going to really mess up your results, okay? And so, when we use higher order schemes, we're going to mostly get rid of this, and we're going to kind of see why we do that. Okay. All right, question. Yes, so there is something better. Yes, so we're going to go over that something better, right? So can we get the components of the velocity or rotate our grid to be normal to that velocity? Yeah. So that's one thing that you can do, right? And so if you have a velocity like this, you can kind of rotate your problem such that it kind of aligns with that grid, and so that's fine. But what if you have a problem where the velocity directions are constantly changing with time, right? And so maybe at one time the velocities are going this way, but maybe another time they're going that way, okay? Or even more simply, maybe you have a case where the velocity it might not be changing with time, but it changes with position, right? And so if you have a velocity that kind of curves like this, right, you can't make your grid into a giant swirly, right? And so it's kind of impossible to kind of do that all the time. Yeah. So it's so rotating the grid, for very simple problems with just the velocity going in one direction, you can do that. But actually, believe it or not, I think the simpler thing would be to do these higher order schemes, because if you rotate your grid, then you also kind of have to rotate your boundary conditions too, and so you kind of have to be careful about how you treat those. Okay. All right. So any other questions on this? Okay. And so for the first part of this of these lecture notes, I'm gonna stick mostly with finite differences, and then after that, I'll show you how to do a higher order scheme with finite volumes. Okay. Okay. And so let me write down the convection derivative here. And so let's stick to just kind of 1D for now. Okay. Right. And so if we have a first order derivative like this, the way that we can discretize this that we've learned is we can do a central difference scheme like this, right? And so this here is central difference. And then what we know about the central difference scheme is that it's second order accurate. Okay. All right, and so for just a second, let's kind of remind ourselves what it means to be second order accurate. Okay. Right. Because if you kind of think kind of way back from kind of when we first, we were just kind of babies in this class, right? So we were just going over what finite differences were in general. And if you kind of remember one thing that I did back then, which has been memed to this point, was we did a Taylor series expansion of this. Okay. And remember, the reason we did a Taylor series expansion was to evaluate the leading error term. Okay. And so just to kind of jog your memory, the leading error term for this was this. Right? Something like this. Okay? And so the first thing we had was a delta x squared, right? And so that's usually the thing that we focus on, right? And so the fact that our leading error term was delta x squared means that we have a second order accurate scheme here, right? But the part that often gets neglected is what is multiplied to, right? Because remember, it wasn't just delta x squared, it was also multiplied by d squared phi dx squared, okay? And so it's not just the delta x squared, it's actually this entire thing together. This right here is our leading error term. Okay. There might have been like a divided by 2 or something like this, but it doesn't matter, okay? Okay. And so, our leading error term is delta x squared times the second derivative of phi, right? And so what other thing that we know, what other thing that we've seen in this class that's also a second order derivative of phi? Okay. And so the other thing that we've seen in this class that's also d squared phi dx squared is our diffusion term. Okay. And so this is kind of the explanation of why we get the cross-stream diffusion to begin with, right? Because we're using this scheme for convection, right? If we're always accumulating this error that has the exact same mathematical signature as our diffusion term, that means those errors are going to pile up on that diffusion term. Okay, and so that's kind of the reason here that we get that cross-stream diffusion, is because both the leading error term and our diffusion term have the exact same derivatives of phi. Okay, and that's not good, and so we don't want that. And so the way that we're going to eliminate this is we're going to increase the order of accuracy for the scheme, and then basically make sure our leading error term is not this. Okay. Okay. Right, and so we're out of time, and so let me, I'll give you kind of just a very quick preview of where we're going. And so instead of having a scheme that's second order accurate, what we're going to use is we're going to use a scheme that's fourth order accurate. Okay. Right. Okay. And so, but that's going to come at a cost, right? And so extra accuracy doesn't come for free, and so we're going to have to work a little bit harder to get these schemes. And it's going to lead to more logistical problems than anything, but we'll cross that bridge when we get there. Okay. Okay. So we're out of time today, and so we'll pick this up again on Monday. So thank you guys for tuning in today. Remember, Wednesday is the midterm, and so if you want to come in on Wednesday, I'll be here to answer your questions, or you can just take the exam in the comfort of your in the comfort of your apartment without, or comfort of your room without having to look at my face. So either one's fine, right? And so if you're coming on Wednesday, I'll see you on Wednesday. But if not, I'll see you on next Monday. So thanks, guys. All right, Juan. So to answer your question, I do have a GitHub account, but I don't really publish anything. I use it mostly to follow some open source projects. All right. Yeah, see you guys. Have I ever messed around with deep learning? No, I haven't yet. It's definitely a hot topic right now. That's for sure. One of my research students actually did a little bit of machine learning. I don't think he didn't do any deep learning. I don't think he just used convolutional neural nets. But to be honest, I don't fully understand all the details of what he did. Yeah, very very popular. Yeah. Yeah, for sure. Yeah, I'd love to see. Oh yeah, yeah. Medical images with deep learning, I think, is really cool. Oh yeah, I'm sure it is. Yeah, I had one colleague that was doing it before, but yeah, let's talk another time and we can see. Mhm. All right, thanks guys. Have a good evening.